Okay, so we're looking at a CD lab here, and we've already talked about diffraction gratings in the past few days. Diffraction gratings act just as a double slit, which is d sine theta equals m lambda. And the idea is that, when light is passing through a double slit onto a viewing screen, it can interfere with itself destructively and constructively. So we get these kind of like bright fringes or bright dots. And then we get these dark points here. So it's kind of like a, you have no idea how hard it is to draw these. Okay, so we get something like that. If we jump into the lab real quick, so let's go lab side. If we jump into the lab, we're kind of in a dark room here, so it might be a little, hopefully you'll be able to see things, and the mic might go down a little bit because I'm kind of stepping away from it. But if we take a look at this laser pointer, so there's the laser on the wall, we can kind of see the dot. We know that if we pass it through a diffraction grating, something like these old glasses that I showed in the prior videos, these are glasses that make lights around Christmas time look all sparkly. But if we look beyond them, we see that we have this kind of a lattice, square pattern on the wall, where we have a central bright light, and then the lights to the side of it kind of dim as it goes in intensity. And we actually see 1, 2, 3, 4 lights there in person. Maybe you see a little bit less on the actual video just because this laser is very bright and you might not be able to get everything there. But this is just a diffraction grating splitting that light in a very similar way to the Young's double slit. Now what we're going to do here is we have a CD. Okay, this is just an old school classic CD with some data written on the back. And the way CDs actually write their data is a blank CD. A blank CD will have on the back side of it. Here, let's just draw a little CD here, like whoosh, and a little circle in the center. A blank CD will actually just like look like nothing, but whenever you start writing on the CD, what the computer is doing is it's writing in binary, so a bunch of ones and zeros. And I'm not going to get into the exact comp sci method of how a computer interprets that into actual like programming code and items that you can do. But essentially, what's going to happen is the computer is going to etch into the surface. Okay, there's kind of like a little film on the CD, and it's going to just like use a laser to kind of etch into that slightly. And it might have some blank regions and some etched regions, but these just stand for ones and zeros. Now, these regions here are very tightly packed together. So when they're tightly packed together, because they're very small, what this kind of looks like is a diffraction grating. Okay, they're raised edges and depressed edges. So if we actually bounce the light off of the back of the CD, what we will actually see here is a diffraction effect. So if we take this, we kind of go back into the lab and shine the laser pointer onto the CD. So I'm just shining the laser pointer onto the CD. We're going to see the light bounce off of it, and when it bounces off, we see this diffraction. And you can see kind of over on the left side, kind of under the lamp right here to the left of the car, that's the bright fringe. And then you should see 2 green lights to the right of it. One kind of to the right of the car, and then one way, way over by the hawk. So how would we actually figure out what the spacing of these little embedments, the ones and zeros, are on the CD? Could we actually figure out just from this diffraction what the data spacing is on the CD looking at that? And it turns out that we absolutely can, but there's a few things that we got to be careful about. So if you just took a ruler, like there's no way you can just take a ruler and figure out the data spacings on that. It doesn't make any sense. But what we can do is this. We can use this double slit equation or a diffraction equation, and we can actually figure this out, where the slit spacing is this value of d. Okay, and it's not going to be perfect. It's going to kind of be an average because some of these slits have small gaps in between them, and some of them are more tightly packed than others. But in general, we can figure this out. And one of the things that we have to, if we kind of draw a diagram of what's going on here, what we can generally see is that if, here's the CD, and then here is our viewing screen. When we reflect this laser light, we see a central, bright fringe, and then we see to the side of it, so here's our central maxima, and we see to the side of it a fringe, and then we might see like a second fringe out here, okay? So normally what we could do is we could say, hey, we could figure out a few things here. If I want the equation d sine theta equals m lambda, and I'm solving for d, I actually want to say m lambda over sine of theta. And if you're doing this, then what you might want is this angle, because we already know m, right? If we look up here, this is m0, and this is m1, and this is m2, and on this side, this is just -1, -2, because it's symmetric. In order to get that angle, though, if our laser pointer is shining out from back here, we need to say, okay, if I make a triangle, I need to be able to find an angle for the first fringe, and then I need to be able to find an angle. Let's use orange. I need to be able to find an angle for the second fringe. But in this case, that means if you have this triangle here, you need a length you are away from a wall, and you need some like width here, right? You need the width of these spacings. And this is where you have to be a little bit careful. If we're being a little careful here, here's why you need to be careful doing this. If you are holding this laser and you're reflecting the light off of the CD, then what may happen is if you're accidentally holding it at an angle, you could get your light to appear on the wall. But if we take a look at this here, let's aim it just like this. If we take a look at this here, the central fringe, that m equals 0, is just about where the car is at. Okay, it's just left of the car. The first fringe, that -1, is over by the lamp. Okay, it's just on the lamp side. But m equals +1, the symmetric point, is all the way over by the hawk. And if you're looking at that, those distances are not the same. What we actually have just done on accident in our lab, if we weren't paying attention, is instead of creating this very nice and symmetric setup here, what we actually may have accidentally created was a setup where we have our bright fringe, M0, and then you might have a like -1 here, and then a +1 way over there. And that's not symmetric. That's not what we want in this lab. It's very, very important that if we were to set this up in the classroom, that we don't actually create something where the CD is hitting at some angle here, so that when the laser light bounces into it and then it diffracts off, some of it does that, and then some of it does this, because these widths are not even close. Okay? So we want to make sure that we have something more similar to the left, where everything is nice and symmetric, rather than the right. Now, there is a way to kind of get around this. You could try to add up your widths and then divide by 2 to just take like an average. But that's probably not a great way to do a lab experiment like this. You probably want something where you just set things up appropriately and bounce them through. And what students have to do is normally they have to figure out a way in order to do this. Best ways to do this are you actually take a sheet of paper, and the way this is actually set up is this is a sheet of paper. You cut a hole into it here, and then you put your CD over here such that your laser light goes straight, hits the CD, and then it diffracts back and it hits your fringes like that. Okay, that's actually the best way to do it. So your actual laser pointer is back here facing this direction. So it's a kind of clever way to do this lab. So students kind of have to figure out on their own. But hey, we're stuck here in COVID world, so we're doing our own little thing, right? So once you get this, you get these points, you can set this up and solve for D. And what we actually see is, I believe that our value of D here for most of this is on the order of, I think it's on the order of micrometers, question mark. It's been a while since we've done that lab, about an entire year. Actually, a little longer because COVID last year. But it's either on the order of micrometers or nanometers. It might be nanometers, actually. But it's a very, very small distance to do that. Now, one of the other things that we take a look at whenever we do this CD lab is a lot of air propagation. And the air propagation that we normally look at is rather interesting because it shows you just how precise our measurements actually are if we're just taking something like a ruler and measuring distances on a wall with a laser, or rather, we're measuring laser distances on a wall. So if we actually do an air propagation on this, and if you haven't taken a look at the air propagation videos that are on the channel, go take a look at those. Those are listed in like pretty much every AP section at the bottom. They're arguably also the most popular videos that people watch on the Coach Bots or YouTube. But if you do an air propagation, there's actually a number of steps that have to occur before you can do anything here. And the reason being is that whenever we're taking a measurement, that measurement has an intrinsic error associated with it. If you have a ruler, you only know so much precision on that ruler. You only know it down so far. So what actually happens here, if we take a look at the equation d sine theta equals m lambda, is the following. First, I need to try to find this value of theta, which means I need a length and a width, just like we stated. And that will allow me to find this angle. So what actually happens here is to find the angle, I need to take the inverse tangent of that width divided by length. Well, what you're actually doing is that width itself has an error to it. It's a plus or minus, error value of that width. And the length, because you measured it, it also has some error associated with it. So before you even find that angle, you need to take the air propagation of this division right here, okay? So this is a division air prop. So that's the first thing you need to do. You need to do the division air propagation. This will then give you the inverse tangent of some quantity, let's just call it Q for right now, plus or minus the error on that value Q. And this will equal some theta. Well, because this tangent is a function, you technically need to do an air propagation on this as well. Functions are kind of interesting to do air propagations on. If you want to do them properly, then you're going to need to know how to do partial differentials, and we're going to just avoid that right now. That's more of a collegiate level thing. What we're going to just generally assume is that because we are looking for the inverse tangent of some value and then points pretty close to that value, we're just going to generally assume that if we funnel in this air propagation for a function around a linear point, we can essentially say that, if I have this point and then 2 points close to it, this is close enough to linear that I'll just be able to take it that way. So we're kind of like fudging this number here, but it's all right for what we're doing at the high school level for our air propagations. If you want to do this more robustly, if you're working for NASA or something, then do it the way they teach you in college. But right here, we need to do an air propagation on the function. So this is a function air prop. And when we do this, we finally get a value of theta plus or minus some error value of that theta. And what that means is when we finally start setting up the equation of d equals m lambda, we'll talk about that lambda momentarily, divided by the sine of theta plus or minus this error value of theta, there's a number of things we have to do. We have to recognize that sine of theta plus or minus some error on theta, some d theta, or del theta, this is a function, and I need to run an air propagation on this. So the third thing I need to do is another function air propagation. So there's a function air prop once again. And when I do this on the sine value, once again assuming the linear and kind of like fudging the numbers, we now get down to the point where we can say d equals m times lambda, we'll come back to that lambda, notice how I'm leaving a space, over some number, let's just call it, I don't know, what's a good number here? Let's call it p. plus or minus some error on P. That's whatever the sine term gave us before. Or our laser pointer, if we look carefully at it, it says that it has a wavelength. That's what this is up here. It's the wavelength. It says it has a wavelength of 532 nanometers. But is that wavelength actually trustable? Could we trust this wavelength? Well, there's probably some error on that wavelength. We don't know exactly what that error is, but it probably exists. Now, since they gave this wavelength as 532 nanometers, we can feel accurate that they have a good idea what it is down to the ones position, but we don't know what it is after that. We don't know if this is 532.1 or 0.2 or 0.3 or 0.4. We just don't know there. So what we'll often do, or this could have been like 531.8, right? It could have been that. So what we'll often do is we'll take that estimated digit back here, and we'll say, okay, let's just give it a plus or minus 0.5 in that regard. This 32 can't be an estimated digit for the company and what they're reporting because they're giving that to us. So we're going to go one beyond it because the company at least knows it's 532. We're going to go one beyond it to here. So this will be the wavelength of 532, but then plus or minus the error of that wavelength, which is in our case 0.5. And in this case here, if we actually go all the way back up to the top, we see that we have another division error propagation again. So we can take a look at this right here and then run a division error propagation. So that's our fourth error propagation move we have. And at this point, we now have that the distance of the slit separation D is equal to M multiplied by some number plus or minus the error of whatever that number is. And this is actually where we can end here. The nice thing about M is it is an integer as given by the Young's double slit equation. M equals 0 for the central node, so we're not really worried about it. But for our cases in the data points we're looking at, they're like 1 or 2, or maybe even 3 if you get that many, depending on what CD you're using. And these are perfect integer values. They have infinite precision, so we don't have to worry about them. We can simply just multiply and scale up our values here. So there's not really anything to change. We just simply scale them up and we're fine. And that gives us our final answer of the actual data spacing on the back side of a CD. And all we needed to do that was to measure from a ruler and some points on the wall. We just had to say what is our length away of our laser for a kind of a bounce off the CD to the wall, and then the width of it. You don't actually have to measure twice the length here. Some people think that you have to measure down and back, but you don't have to do that because what you really care about is where that diffraction is taking place. You care about where it hits the CD here and then where it comes back to the wall. So you only care about that return trip on these. So as long as you can measure these widths and lengths here, the separation of the fringes and then how far away you are, you can use the double slit equation and some careful error propagation in order to give yourself a really, really, really good estimation on what the data spacing on any CD or Blu-ray could possibly be. And that's kind of a wild thing considering that, you can buy any laser at like a dollar store and you've got a bunch of CDs just sitting around your house. So that is the finish. That's kind of the rundown of the CD lab and how we would do it. Like I said, if you haven't seen those error propagation videos, go check those out on the channel. It's its own little thing, its own little world for that. But until then, adios and take it easy.